Let's do some sensitivity analysis for the assembly plant optimization. Okay, in two previous videos, we came up with the graphical solution for the assembly plant. If you recall, we have an assembly plant that has a body shop operation, a paint shop operation, and then the final assembly. And we drew this in Desmos. And so we found the feasible region, right? So we have these three constraints, which are less than or equal to. We found the feasible region and the efficient frontier. And here we have the objective function, which was the daily operating profit. So we make 1,000 operating profits, $1,000 for each compact car and $1,300 for each compact SUV. And here's our Z line for our objective function when we're making $620,000 per day. So everywhere along this red line means you're making $620,000 a day. And that is just tangential to the feasible region at the value here of, let me see if I can get this highlighted. No, I can't. Okay, at the value of 100 and 400. So the optimal solution occurs at 100x and 400y, and at that point we're making $620,000 per day. Now, the sensitivity analysis is an extra little bit you get out of Solver for nothing. And so if you went to our Solver sheet, we had clicked sensitivity analysis, and it comes up with this. There are two major parts. One is called the variable cell, which is our objective function. It'd been nice if Solver would have said objective function. Here's the final values for my X and my Y number per day. It's kind of neat how they do that. 100 and 400. And here's the objective function coefficients, 1 and 1.3. And that's what we have here. And if we have 100 and 400, we'll be making 620. Now, the allowable increase and allowable decrease, we can't really see that very well because it's off the page. I guess I can move that over a bit. Okay. Tells you how much you could change this coefficient of 1 without changing the final value of 100 and 300. And so I can move from 1 all the way up to 1.3 without changing these final optimal solution. But what will change is how much money I'm making. I can do that. So let's say we're going to make an extra $100 for every compact car. So that's 1.1. You can imagine gas prices goes up, and so people are more interested in cars than SUV. And if you saw that, you saw that the line tipped a little bit. So if you just focus in on that red line, just focus here. As I change that coefficient, the red line tips a little bit, right? And so it's saying how much I can change that red line and still have the optimal solution there. So if I make it was originally 1, right? So the red line's right here. If I change it to 1.2, I'll be making a little bit more. And so I'll be making 0.2 times 100 is 20, so it'll be 640. Okay, and that's where the optimal point is right there. Now, if I change it too much, if I go beyond the allowable increase from 1 up to, let's say, 1.5, what will happen? Well, it tips so much that this is no longer the optimal solution, and my optimal solution will be this point over here. I don't know if I can find it or not. Let's try 650, 660, 670, 680, 690, 700. Am I getting closer? I'm trying to get up to there. 710, 720. Okay. And that will be the optimal solution. So what that means is if I go above this allowable increase, basically I have to run Solver. The optimal solution goes from this particular quarter of the feasible region, right? This particular corner of the efficient frontier. And if I change the coefficient too much and makes cars too attractive, I start to make many more X's than Y's, and I jump over to this corner. So that's what this allowable increase and allowable decrease is doing here. Same thing for how far down you can go, right? So let me just go ahead and put this back to the original values. Okay, 620. All right. Okay. And you have the same thing for y. Works in the same way. Now, you can only change one at a time. If you say, hey, what happens if this goes up to 1.2 and this goes up to 1.7, what will happen? I wouldn't know. I'd have to rerun solver. Okay, so that's with the top part with the objective function. The bottom part is interesting and tells you what we'll be looking at is the shadow price, right? But this has to do with the constraints. It tells you what the final value was, 3,000. We're using 3,200 hours in the body shop, and we have 3,200 hours in the body shop. So this is binding. Body shop is binding. The slack is 0. In the paint shop, we have 5,000 hours, and we're using all 5,000 hours. So the paint shop is binding. But in assembly, we have 3,800 hours, and we're only using 3,200. So this is slack. This is not binding, and the amount of slack we have is 600. Okay. Now, what's really interesting about this is the shadow price. And the shadow price tells you, hey, for this body shop, if we have an additional hour of body shop time, what will happen to the optimal solution? Well, it will go up by 0.1. Now, these are in thousands, so it'd go up by $100, right? If we had an additional 10 hours of body shop time, this would go up by 0.1 times 10, or $1,000, right? And we can just keep on increasing that up to 300. So let's say we have an additional 100 hours of body shop time. Well, then our objective function will go up, our final objective function will go up by 0.1 times 100, or 10. Okay, so we can go ahead and do that. Let's go over the body shop and let's add an additional hour. Oops, where's my body shop? That's the one down here. This is what, right? 4 and 7, 3,200. So if we have an additional hour, if we add 100 hours here, shoot up to 3,300. Okay, what's happened? Well, we moved up this constraint, right? This constraint moved up, which means, would it be this way? Be this way. It has moved up. And so now, let me take that off. So now it's moved up, and here's where the solution is, right? And now I can move the solution up, okay? And how much should we move the solution up? Well, it was 100 times 0.1, gotta do my math, is 10, so it moves up by, that's up to there, right? And so you see it picked up that corner again, right? But if I move it up too far, right? If I go above 300, we only went up 100. We can go up to 300. So was it 300 plus 3,200 is 3,500. It moves up even farther, right? That constraint moves up even farther. And now we have to move up, was 300, and I'm getting my numbers mixed up. We can get more here, 65, okay? And now we're up at this corner point. If I keep on adding more and more body shop time, what happens? It no longer becomes binding, right? And so because the body shop line is up to here, it's not the binding constraint anymore. What you have is the paint shop and the final assembly, or the binding constraints. Could be the binding constraint. And so we would just stay up here, right there, right? So I moved it up. I increased too much. Okay. Now I don't know if I'm smart enough to go back and set this back to, was that the right one? Which one was it? 38? Oh, 37. This goes back to 3,200, right? This is the original problem. Okay. And so this would go 620, was it? Yeah. Okay. So that's the shadow price, and you can see how it changes on the figure. Okay. One last thing, the shadow price for assembly is 0 because I already have assembly slack, and so if I add an additional hour of assembly time, I'm not going to use it, and so the contribution will be 0. Okay, so the shadow price is a very important concept, not only for doing these kind of like technical work, but it's also as a, if you're thinking about strategy or other things about your particular business, shadow price is very important. It kind of like gives you what your valuation is for an additional amount of resource, right? So if I'm looking at body shop, an additional hour of body shop, what's the value to me, right? The value to me is 0.1, okay, for an additional hour. What's the value of an additional hour paint shop is 0.006, right? And then I can compare that to the cost of getting those additional values. What's the value to me as the business person of an additional hour of assembly? It's nothing. I'm not using all my assembly time, so it's like I'm not using it. Okay, so this sensitivity analysis can be very valuable. You can relate it back to, in these simple problems with two decision variables, you can relate it back to the graphical solution and see what happens as you change the parameters. When you change these guys up at the top for the objective function, what you're doing is tilting your z line, and that can pick up different solutions. And if you change these guys, the shadow price means you're changing the right-hand constraint. You can see how how much money you're making changes. Okay, great. I hope this was a useful video, and I will be seeing you in other videos.